if we look back at our first slide, so we're right here, right? If I'm approaching C, minus 3 is discontinuous. So in order to figure out why it's discontinuous, let's figure out what value of x is going to make it discontinuous. So right away, when I look at this function, I notice it's a rational expression. Okay, it's rational, meaning my numerator is an expression and my denominator is an expression. Now, you should know at this point that your denominator can never be 0. So I'm going to set my denominator equal to 0 to figure out when my function doesn't make any sense. So if x minus 3 equals 0, that means my function is going to not work when x equals 3. So at that point, x equals 3, or at the line x equals 3, there's some sort of discontinuity in my function. I don't know if it's a step discontinuity, I don't know if it's an asymptote, I don't know if it's removable, I don't know what it is, but I know it's somewhere around x equals 3. So go ahead in your calculator and graph our function, x squared minus 9 all over x minus 3, this function, and sketch a graph of it in the space provided. As you're sketching the graph in the space below, make sure you figure out what type of discontinuity occurs in the graph. If there's a hole in the graph, make sure you draw a hole. If it's a step discontinuity, make sure you visibly show me the step. And if there's an asymptote, make sure you put a dotted line there. I'm going to go through those graphs with you tomorrow in class. So let's move on now and look at what's happening below. Okay, let's look at each of these graphs and let's figure out if we can determine if the graph, or if our function f of x is continuous at C. Okay, so if I look at this first graph, I want to know if my graph is continuous when I approach, or at the point C, excuse me. So at the point C, is my graph continuous? So if I look at my first function, at my point C, my graph has a hole in it. Okay, so this is not continuous, it is discontinuous, or you just write not continuous. It's not continuous because it has a removable discontinuity. Okay, removable. Okay, so removable discontinuity right there. Remember, removable has one hole. We can easily fill it in. Okay. Let's move on now to this graph. Is it continuous? At C, at my point C, does my graph continue? No, it doesn't continue. It stops there, right? C is my asymptote. So since I can't ever cross an asymptote, I know that my function is discontinuous. So we can again write not continuous. Whoops. Not continuous because it has an asymptote. Great, moving along. Okay, let's look at our next graph. So this graph right here. So again, at the point C on my x-axis, is my graph continuous? Is my function going to continue through this point? And in this graph, it is. So yes, my graph is continuous, or we could write continuous. Either one works. Okay. Now the other thing is, notice how my graph reaches a nice point right here. This point is called a cusp. So just so you have that for reference, because it will be handy when we talk about derivatives, that point is called a cusp. Okay? So anytime you have a corner or a bend or a sharp point in your graph, it is a cusp point. Okay, moving on. Next one. If I'm at C on my x-axis, does my graph continue through this point? Yes. So this is also continuous. Fabulous. Next one. So again, I need to figure out on C, is my function continuous? I want to make sure that there's no break in my function. So as I go up to my line, I see that I have a hole there. But if I continue, I also see my hole is plugged right there by that point. So it is a removable we already know it's a removable discontinuity because of that point. Do not let this point fool you, okay? If you have to lift up your pencil to get to another point on your graph, it is no longer continuous. So that's what I would have to do here. If I'm drawing this line, I would draw it, put a dot here, and then continue. Okay, so again, this is a discontinuous graph with a removable discontinuity. Discontinuous with removable discontinuity. Great. Okay, and our last one, if we are looking at point C on our graph, and we go up from C, I have a hole, and then I have to keep going up, my hole's plugged, and then it continues on, okay? So again, right away, you should notice that this is a discontinuous graph, right? If I take my pencil to draw my graph, I draw it here, I have to lift up my pencil and then continue. As soon as you lift up your pencil, your graph is discontinuous. So my last graph is discontinuous because it has a step discontinuity. Step discontinuity. Great. Okay, and we are on to the next. Okay, so let's use the examples we just looked at to figure out the definition of continuity. So at a point, we're first going to look at continuity at a point. So function f is continuous at the point x equals c if and only if the value of your function at f equals c exists, the limit as x approaches c of f of x exists, and the limit as x approaches c of f of x equals f of c. So it's really, really important that when you check your limit for number 3, that should be the same answer as you got for number 1. Number 1, the value of c, the value of your function at c should be the same as the value of your limit as x approaches c, okay? So that happens if you're continuous at a point. You're continuous at an interval if every value, so the function f is continuous on an interval of x if and only if it is continuous at each value of x in the interval. So every single point in your function would need to follow these 3 properties in order for your function to be continuous. If there's one point in your function that doesn't have all 3 of these properties, your function is no longer continuous. Okay, so far in this class we've looked at limits. If we've only looked at one set of limit, right? It either exists or it doesn't exist. Now we're going to look at what happens when we only approach a limit from one side of our value of c, okay? So let's look at the graphs below, and we need to figure out if we can find the limit as x approaches c of f of x, okay? So it doesn't matter if a function is continuous or discontinuous when you're looking for a limit. A limit can exist even if a function's not continuous at that point, because you're not actually going to the point, you're just getting as close as possible to the point, okay? So as I approach c on my x-axis, it doesn't matter that I have a hole in my function, okay? Because my limit doesn't care about a hole. All my limit cares about is as I get closer and closer to the hole, what is my value of my function getting to? So as I get closer and closer to my hole, on my function, the value of my limit is 3. Now remember, you need to make sure that you're checking both sides of the hole, okay? So as I get closer from the left and as I get closer to the right, it doesn't matter, the value of my function is still 3. So I can say, so can you find the limit? Yes, I can. Yes. Okay. And the limit as x approaches c of f of x is equal to 3. Okay. For the second one, as x is approaching c on the left, we're getting closer and closer to 4. But if we check the other way, as we're approaching from the right, we're getting closer and closer to 7. So since I'm going to 2 different points on my 2 different values on my graph, this limit does not exist. If we look at our last example, as I'm getting closer and closer to c on my x-axis, my function is getting closer and closer to 12. Okay? as I'm going from the right, my function is still getting closer and closer to 12. This point is the value of my function at c. But I'm not looking for the value of my function at c. I'm looking for the limit. As I get really, really close to c, I'm going to 12. It doesn't matter that it's only defined at 18. I don't care where it's defined. I care what I'm getting close to, okay? So again, this limit does exist. So the limit as x approaches c of f of x does exist, and that limit is 12. So when we think about a limit, we know that we have to think about what happens from both sides of our function. So when we do that, it's called a left-handed and a right-handed limit. So as we look at let's look at this notation. So if you look closely, we can say the limit as x approaches c, and it has a minus sign. This minus sign means that you're approaching from the left side of c, okay? So as you're approaching from the left is their function. This is called the left-handed function, limit of f of x, okay? So we can write that down. So we can say that we are dealing with x as it gets close to c from the left, okay? Or you can also call it the you can also call it the left-handed limit, okay? It's left-handed. Okay, so when I look at my next notation, it says the limit as x approaches c with the little plus sign of f of x. So that's when x approaches c from the right. From the right, and that is a right-handed limit. Handed. This doesn't look like a D. A right-handed limit. Great. So go ahead and try example 1, or this example on your own, and I'm going to check it tomorrow in class. Keep in mind that for each of these functions, I'm only defining this linear function when x is less than 2, and I'm only defining this quadratic function when x is greater than or equal to 2. So as you are drawing your graph, if this is x equals 2, one function here should stop and another one should start, okay? This function, my linear function, will not cross my line x equals 2, or x equals 2. It won't cross it. It's going to be less than that. So you also want to make sure that at the end of that line you put a circle to denote that it's strictly less than 2. And for your quadratic function, you want to make sure your endpoint is a filled-in dot to denote that it's strictly it is greater than or equal to 2. Okay, so go ahead and do that example on your own, and I will check it tomorrow in class. Okay, so go ahead now and pause the video if you need to so you can do that example. I'm going to move on to the very last page of your notes. Okay, so on the very last page of your notes, C is continuing from the previous page. And then notice this box right here. This box is extremely, extremely, extremely important. We can draw a little squiggly around it, okay? So your limit of a function, whatever your limit is, 12, 19, whatever the value of your limit is, only exists if your left-handed limit and your right-handed limit are equal, okay? That's really, really important. Your limit has to equal the limit, I'm sorry, I miswrote. Your limit has to equal the limit as x approaches c from the right of f of x, which also has to equal the limit as x approaches c from the left of f of x, okay? It's very, very, very important. If one of these values is different, if your left-handed limit is different than your right-handed limit, your limit does not exist. If you have any questions, write them down so you don't forget, and I'll answer them tomorrow in class.